In this sequence, we're going to talk about data augmentation. So what is data augmentation? Data augmentation is a data processing step that increases the amount of available samples or data by performing transformations on the original data. Examples would be cropping, padding, flipping of images, or maybe rotating, translating. The challenge is that the transformations should preserve the original labels, annotations of the data. So what we see here on the bottom right is an image of an orange that is flipped. And looking at the flipped image, it looks as much as an orange as the image to the left. This is a successful application of augmentation where we now have one more image and the label stays the same, but the image is different. A counterexample is shown here on the bottom left. By taking this 6 and rotating it, it becomes a 9, and this is now incorrect to say this is still a label 6. So by applying this transformation here, we would in fact also have changed the label of the data, so this is not something we can use as a data augmentation strategy. So in general, we just want to apply data augmentation to improve performance. And in computer vision or any type of application that deals with images, we're often plagued with the fact that we do not have as much labeled data as we would like to have. And data augmentation is one strategy that can help. One can think that data augmentation teaches the model about invariances in the data. For example, an image and a flipped image is some type of invariance, and by applying this transformation, you teach the model that it should be invariant to images being flipped. Then data augmentation should reduce overfitting and improve generalization. The hope is that especially again, if the data set that you train on is quite small, that by applying data augmentation, the generalization performance is better. So we are going to just show quickly a lot of individual transformations that can be applied to images and be used in data augmentation. Image transformations are typically parameterized, and these parameters are denoted as magnitude below. This is a table copied from a paper that I'm going to show next. I'm briefly just going to read the names, and hopefully you can imagine what these transformations do, and later maybe you can read this again more carefully. So horizontal flip, vertical flip, zooming, cropping, shear in the X direction, shear in the Y direction, translations in X and translations in Y, image rotation, auto contrast, invert, inverting the image, equalize, solarize, posterize, contrast, color, augmentation, brightness, sharpness, cutout, and sample pairing. So we will go over these, or at least some of these. What can happen if you apply a transformation to an image, that there will be new pixels entering the image frame that you need to find some color value for. So this is just text describing the image in the next slide, and I'm going to just talk about the image. So what you see here is an image of a bunch of spheres that have a face kind of painted on them. There's one smiling face in yellow and a bunch of sad faces in blue. And the original image has been rotated. And what you see here way to the left is the image in rotated form. And the gray parts here, 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 and here are new pixel values that need to be filled somehow. By applying these transformations, we obtain these pixels here where we don't have a color for. And this image here way to the left already shows the first strategy, which is filling the new pixels with a 0 value. Now why this is not black is because it's 0 in the transformed color space, and if we are then we have to visualize somehow. So this is a 0 value in transformed color space. In this image here, the second image to the left, we're simply copying the pixel value from the pixel that is closest to the boundary. And we can see, for example, to the lower left here, we're actually quite lucky. That looks really reasonable fill-in. I mean, not really great, but considering how trivial this algorithm is, it seems to at least maintain the characteristic of the image quite well. Also this, quite reasonable, again, considering the simplicity. Maybe here, this might look a bit different, but still, I mean, the colors are the same. It's a possible option. Next, the third image to the left, we're going to reflect the pixel values at the boundary. So there's some unknown pixels, and so we're gonna copying. So you see that here, you know, these filled in values, they're kind of copied. So the further out you go from the further inwards to the boundary, you're copying. Next, what we have here, it's almost the same as here. The difference is only that we're copying the edge pixel as well. So there's going to be a 1 pixel difference where we have where we can make the decision if we're going to copy the edge pixel itself or if we just start copying from 1 pixel next to the edge pixel. So this last example shows a kind of some of the copied wraparound, so it's wrapping. When we go out here and want to fill pixels in here, we're actually copying them from this region here. And if we want to fill pixels in this top right corner, we're copying from this region here. You can see that the wrapping does a reasonable job maybe here and here because the scale of these spheres is quite similar, but it doesn't do that great a job when we copy these very small balls here, but actually here through the perspective we have very large balls in the image. So we're going to use this image to illustrate several of these transformations. Alright, so brightness, here the image gets a bit darker, here the image is like here's probably quite a bit darker, this is a bit darker, maybe here slight similar or maybe a bit brighter. So these are just 3 randomly selected changes using brightness, and then also in the following you see 3 random augmentations using a particular transformation. This is horizontal flip. Alright, looks fine. Horizontal shift. Now here again you notice that we have this fill-in pixel problem. So here the parrot got shifted to the left. That means these pixels are filled in. And because this is such low frequency on the boundary, and then just by copying the pixels, it's actually hard to notice even that pixels have been filled in, so that has been quite successful. Here a shift to the right, pixels are filled in, that's quite a bit more noticeable. And so this is the boundary here, everything to the left of this boundary is kind of this pixel copying by copying the value closest to the boundary. Vertical shift, the same, parrot moves up, so we copied pixels here, and the parrot moves down. So this is again more successful. It's quite difficult to actually see the boundary here. Zoom, that's kind of zooming in and rescaling. So here we zoom in more and the parrot's head becomes bigger. Rotation, again you see here some filled in pixels. So now the head changes, kind of the parrot is either more sideways or more upright. All right. So actually I'm gonna quickly show one of the libraries to do data augmentation. This is called Augmentations, and this is on GitHub. So I'm gonna do this fairly quickly. So here you see some other examples of augmentations, for example, shuffling the color channels, and several types of color changes such as RGB shift, hue, saturation, value change, some random gamma change, blur, and so on. Let's also look at this example. This would be some form of a distortion using a grid or some elastic. This is a grid distortion, and this is an elastic transformation where the image can change considerably. It kind of has this type of wobbly effect on the image. Also, a bit further up, you can click on this link to go to some Colab notebook to try out some of these things yourself. So here we are in this Colab notebook, and I was gonna scroll down a bit where this is the original image that is going to be used, and then you come to this kind of interactive notebook where you can try out the strength of the parameters. Looking at this example here, I had to execute some of the code first. You could now go and move the slider to see how the image is affected. Doesn't work terribly fast, as you see, but as expected, high brightness increases the brightness. Let's also look at this example, JPEG compression, that creates JPEG compression artifacts. So as you see here, this kind of blocky quantization, that is a compression artifact that could also be used for data augmentation. Okay, now let's go back to CutOut, a paper by DeVries and Taylor, or similar paper by Song, that will again explain just using the image on the next page. The idea is to make the classifier maybe more robust to noise or change, or more robust to the generation of the input images, and therefore we can cut out a square in the input image, somewhere in the input image. So for example, here you see a red car, and then this grayish region, this is a square that's being cut out, and the values are again set to 0 or maybe 0.5 to some constant value in the transformed space. So just to clarify, 0 in the transformed space means it should be kind of the average color. That's why it shows up in gray around the 0.5. But in transformed space, it's going to be a 0, as they're going to be the smaller values than this kind of average color will be negative color values, and the values that are bigger than 0, these were the ones in the original images that were larger than this average pixel color. So this region, of course, could be made a lot more complex. So what we see here are squares, but why use squares? Why not use rectangles, or why not use some sort of blobby regions, maybe convex regions even, or some other blobby regions that are not too crazy? And here the authors argue that in their experiments, just cutting out squares gives as good results as any of the other variations that they tried, and therefore they just recommend the simplest version, which is cutting out squares. Sample pairing is a completely crazy augmentation strategy. It's so crazy that I actually find it hard to believe that it would work. The authors propose to take two input images, I1 and I2, and linearly blend them together. So in this equation, you can think of I1 and I2 being rank 3 tensors describing an image, and multiplying such a tensor with a scalar value alpha just multiplies each scalar value inside this image tensor with this scalar alpha. And 1 minus alpha times I2 means that every scalar value in this tensor I2 will be multiplied by 1 minus lambda. The simplest choice for lambda is to use lambda equals 0.5. That means that both images will be combined together with equal importance. The interesting design choice here is that the authors simply keep the label of image I1 as the correct label. Even though two images I1 and I2 are blended with the same weight, lambda equals 0.5, the authors propose to simply keep the first label as the correct one during training. Also, image pairs are selected randomly from the dataset without considering class labels. The authors report that pairing images from identical or similar labels degrades performance. I would find that to be very counterintuitive. It seems that maybe pairing label images from the same class would at least not hurt. If this crazy thing works. Now, the paper also proposes a schedule where they interleave epochs with sample pairing and without sample pairing. And at the end, they fine-tune without sample pairing. Here's an illustration of the pipeline. Two images A and B are selected from the training dataset. Both of these images undergo basic data augmentation. What is this basic data augmentation? First, out of this 256 times 256 image, a 224 times 224 patch is extracted randomly from within the larger image. And also horizontal flipping is randomly enabled or not. This type of data augmentation goes back to AlexNet, the first paper that started the new modern era of deep learning. Then mixing happens, and the mixed patches are sent to the training network. MixUp is, to me, the more intuitive version of this idea. The authors also propose to form a convex combination of samples, so their image tensors I1 and I2, and they also use the same equation, lambda times I1 plus 1 minus lambda times I2. More intuitively, the authors then take the ground truth labels L1 of image I1 and L2 of image I2 and mix them with the same weights as the images themselves were mixed. So if image I1 is a cat and I2 is a ship, then maybe lambda is 0.3 times the cat and 0.7 times the ship. Then the labels, one hot encoded, would for the cat give probability 0.3 and for the ship 0.7. The lambda is sampled from a beta distribution. Particularly, lambda is sampled from a beta distribution with parameters alpha and alpha. Alpha being something between 0 and infinity. Let's just look at how the beta distribution looks like for a smaller alpha. So, for example, for alpha alpha is 0.1, so the beta distribution has parameters 0.1, 0.1. This forms some sort of a valley where parameters, lambda parameters near 0 and near 1 have a much higher chance of being sampled. In this configuration, for example, the blending wouldn't be that extreme. Mainly one image would dominate. For settings 0.9, 0.9, we would basically pick all blending weights almost with equal probability. I'm saying almost because it's not a completely straight line, but it's not that far from a straight line. So far, we discussed transformations that we could consider individual transformations that are applied to one image. Maybe MixUp is a bit more complicated, but let's consider what we discussed about so far as elementary operations, as elementary transformations. Now, we can answer questions about how to combine these building blocks. Maybe we want to apply one transformation per sample, for example, one per image, or we can apply multiple transformations in sequence. So one image could have some contrast change, a rotation, and a translation at the same time before it is fed to the network. Do we want to apply the same transformation for all samples in a mini batch, or we want to sample new transformations for each sample, for each image? Do we assign probabilities to individual transformations or assign probabilities to chains of operations or chains of transformations? So, for example, does rotation have a probability that is specific to rotation, or are we really assigning probabilities to combinations? Maybe translation, rotation would be very frequent, but scale and rotation could be a lot less frequent. That means that transformations wouldn't be independent. Another question is, should we use continuous set of parameters or discrete set of transformation parameters? It seems obvious that continuous is the more evident choice. However, for learning these parameters somehow with some sort of learning framework built on top of these elementary operations, it might make sense to just use discrete transformation parameters. Then it is easier to learn probabilities for individual transformations. We will discuss two frameworks combining elementary transformations, one of them quite complicated, called AutoAugment, and one very simple, called RandAugment. AutoAugment, for example, uses subpolicies that are a combination of k transformations, each with probability of being executed and parameters. But they use only a small number k, so they only use subpolicies that consist of two transformations. So a policy is a combination of subpolicies in AutoAugment, and each subpolicy has a probability of being selected. This is a very general and very powerful framework. Implementing in Python, we already showed the augmentations library. Here are some more commands, just randomly selected, so if you want to go look that up in the documentation, for example, compose, center crop, color jitter, random, affine, just to get some idea how these commands look like. if you don't use this other library. Just to mention that there's a difference between applying data augmentation during training and test time augmentation, which is also an important building block that is used in many machine learning systems. At test time, what you can do is you can apply k different transformations or transformation sequences to an image and feed all of them to the network at test time, and then you somehow aggregate the results. So for example, you could put an image in 10 versions to an image classifier and get probabilities and then average the probabilities of the 10 different augmented images. So one popular method for image classification that was started with AlexNet is to use multiple crops and then average the probabilities. But these test time augmentations differ from problem to problem. It is important again that you keep the same test time augmentation methods than other papers if you're comparing yourself in a scientific paper submission. By contrast, if you're competing in some classification challenge, you want to play around with it until you have a winning strategy and can beat out the other methods. So AutoAugment is a paper by Kubuk et al. And we're first going to look at the results from the paper. The error rates reported are top 5 for ImageNet and top 1 for others. That means for ImageNet, in this type of comparison, you're allowed the top 5 guesses, and if one of your top 5 guesses is correct, it counts as correct. This is how ImageNet comparisons started out, because it was so difficult to guess the top 1. More recent papers are just doing top 1 comparisons. So the competitors you have to look at the paper for, and I think this should be V100 NVIDIA cards actually. Let's just look at the results. We will see that 1, the method can beat state-of-the-art, or at least what is selected as state-of-the-art, and that running this method is actually quite expensive. So for Sci-Fi 10, the improvement is 2.1 to 1.5. For Sci-Fi 100, 12.2 to 10.7. SVHN, 1.3 to 1. Stanford Cars, 5.9 to 5.2. And ImageNet, 3.9 to 3.5. Considering that ImageNet is so incredibly competitive, so many people working on it, and that it's somewhat the gold standard, even an improvement of 0.4% can be considered significant. We are dealing here with a discrete search problem because we need to create these policies and sub-policies. So we need a search algorithm and a search space. The AutoAugment search algorithm is reinforcement learning. This will only be discussed later in the class. The components are a controller, a recurrent neural network, a training algorithm, proximal policy optimization. These two things will make sense if you later study a bit more in reinforcement learning. Other alternatives that could be used instead of reinforcement learning would be genetic algorithms or random search. For these type of problems, it's not really clear how far reinforcement learning is from some other types of random search algorithm. I think what it comes down to is that the network itself proposes policy or sub-policies, and then you run some evaluation and see how well does a particular augmentation strategy work. This result is fed back into the network, and then the network can learn from however well the augmentation strategy did, and then it learns to propose maybe a bit better augmentation strategies. This is extremely time-consuming and extremely difficult to train because you have somewhat a complete network training step in the loop where you need to train a classifier given a certain strategy. Now the search space says how is policy sub-policies configured. So one policy consists of 5 sub-policies. A sub-policy itself consists of 2 image transformations applied in sequence. The hyperparameters here are the probability of applying the transformation and the parameters for the transformation. The parameters and probabilities are discretized into 10 and 11 values, respectively. So what we have is parameters for for example, a translation or rotation. You can't rotate any arbitrary value. You would say, okay, we have 10 different rotations, and then for each of those, we cannot have a probability arbitrary between whatever 0 and 1, but we'll also discretize possible probabilities. Here would be an example policy. What we see is one image is being fed in, and this image is a 15 written on brown background. One policy can be described by what's written below. A shear x is applied with probability 0.9 and parameter 7. Invert is applied with probability 0.2 and parameter 3. What we would expect is shear happens quite often and invert happens quite rarely. Therefore, and this is the slightly confusing part, this is just a random application of 3, and so each image is being fed into this sub-policy. So you don't know is shear selected or invert selected. You kind of have to reverse engineer that from looking at the images. So we can guess that inversion has not been selected for all 3 of those, but shear was selected for all 3 of those. The next we're going to skip. Let's look at this. We have again shear selected with 0.9, parameter 4, and auto contrast with 0.8. So looking at the last one and the first one, this is when auto contrast was applied, and it seems that shear was also applied to all 3 of these images. Maybe let's look at the last one. Again, auto contrast and shear. So maybe here shear wasn't applied and auto contrast wasn't applied, it seems. And then here auto contrast was applied and shear was applied, and up here only shear was applied. AutoAugment is a very expensive algorithm because generating enough samples for reinforcement learning is difficult, and no computation is shared between the samples. So I actually checked it is a P100, not a V100 GPU. So if you would use Google Cloud on demand for a P100 GPU, looking at the table in the paper, it would cost you $37,000 to discover an ImageNet policy. This is quite expensive. So the common application seems to be mainly to transfer a learned policy, for example the ImageNet policy, and use it on other datasets. This is what also the authors propose in their paper. Population-based augmentation is another randomized search algorithm to find augmentation strategies. Let's look at the main part of the algorithm. There's an exploration stage where different workers, so there are many different workers trying to find a suitable augmentation strategy or augmentation policy, and these workers try to modify the hyperparameters to improve the augmentation strategy. And then the exploitation step, in this step, the higher performing workers copy weights to the lower performing ones. Now, this is only the idea at the very high level, just to give you another flavor of paper that tries to learn these augmentation strategies. However, as this paper argues, RandAugment, a lot of this fancy search might be in vain. RandAugment, also called practical automated data augmentation with a reduced search space, says, let's find something that is super simple, very practical, but still works. What they do is they use k = 14 different transformations. Identity, auto-contrast, equalize, translate X, and so on and so forth. And then they perform n transformations per training image. Now, n is a hyperparameter of this method, RandAugment. And for each of these transformations, they selected with probability 1 divided by k. This is different from before, where there was a list of transformations and each had an individual selection probability. Here, when we say we perform n transformations, there really will always be n selected unless you pick the identity with a probability 1 divided by k. Then for this one transformation, nothing will happen. So let's say n is 2, then we would roll a dice and select one of these 14, and then we roll another dice and select another one of these 14. So we get 2 transformations and we apply both in sequence. Now, we can also configure these transformations with an integer strength from 0 to 10. Again, this requires you to map these different strengths to transformation parameters. For example, for the rotation, you would need to find out what's going to be 0, what's going to be 10. So designing these transformation strengths is some work you have to do up front, and this requires some form of probably fiddling around with the individual transformations, because you need to select the strength so that they're somewhat comparable. So a 10 rotation should be somewhat comparable in the way or how strong it is to a 10 translation, whatever that means. And this is some thing that requires human intelligence that needs to be done well for this method, in order for this method to work. Now then there's a second parameter, m. So actually this n should also be read. So m is a second parameter, and so this is basically a global strength. So this same m applies for all transformations. So if m is 7, then the strength 7 will be used for all transformations. This means we have an augmentation strategy that has only 2 hyperparameters: n, number of transformations applied, and m, the strength of the transformations. What the authors propose then is to simply use grid search. The authors also experiment with 4 different schedules, but report that all of them more or less work the same, so just pick the simplest one, which is use an m with constant magnitude. So first schedule is have constant magnitude m, have a random magnitude, have a linearly increasing magnitude, and a random magnitude with increasing upper bound. One thing that the authors argue is that these other methods are so expensive to train that it's actually too costly. What you would need to do, you would need to use these very expensive machine learning algorithms on one data set, because we said could cost you 40,000, and then hope that the augmentation strategy that works also for your new data set, because you need to more or less pick this augmentation policy, this augmentation strategy of whatever the other authors trained, because it's too expensive for you to retrain. And they say that transferring one augmentation strategy to another data set does not work really well, because as they show in their data, in their paper, the augmentation strategy that works well heavily depends on the data set size, where there's a difference between small data sets and large data sets. Also, they report state-of-the-art results with their much simpler strategy. Now, this type of paper you can only write if you have a very large number of experiments. So this group from Google Research are some of the absolute top researchers in practical deep learning. If you look at this paper, RandAugment, you will see that after related work, there's the method description of RandAugment that I went over the slide, and you see that the method description itself is not even one page. So very, very short. However, then there's a large number of experiments to back up this very simple method. So this is one style of paper where you propose a really simple idea and back it up with a very large number of experiments and, which is very important, state-of-the-art results on important problems. This last part is extremely difficult to do. Why? Because in order to improve the state-of-the-art on important problems such as image classification or object detection, you do need to have the state-of-the-art algorithms implemented and running, and this is something that Google has. So here are some other strategies that you could consider for learning data augmentation policies or strategies. One, you could use generative adversarial networks to generate additional data. Or you could use variational autoencoders to generate additional data. These generative models, for example GANs, can not only be used to generate additional data, maybe they can also generate augmentation strategies, maybe selecting transformation parameters. And you could also have another neural network learn the transformations, so you feed in an image and it outputs another image. Without citing any particular paper, these strategies have been tried, but they don't seem to be very common in use, but maybe it's a research direction that could be interesting. We haven't studied GANs or variational autoencoders yet, but we will do so later in this course. Again, my recommendation to look at the Augmentations library for transforming images.